In this video, we'll be configuring the ADC module of the PIC12F683 microcontroller with PICKit 3. First, we'll be seeing the connections between the microcontroller, the shift registers, and the 4-digit 7-segment display. Then, by using the datasheet of the microcontroller, we'll be writing the code in MPLAB X IDE, and in the final section, we'll be observing the conversion of the potentiometer's output to the values between 0 and 1023. If you take a look at our connections, you will see that GP2 is going to be connected to the serial input. GP4 is going to be connected to the shift register clock. And GP5 is going to be connected to the storage register clock. This is nearly the same setup that we did for our previous video, which was the shift register and the 7-segment display. The only difference that we have right now is the potentiometer that we are going to control with the ADC10 module. We are going to connect the output of the potentiometer to the GP1 pin of the microcontroller. We are going to connect this pin to the ground, and we are going to connect this pin to 5 volts. Our VDD is going to be connected to 5 volts, VCC to 5 volts, and for the second shift register as well. And shift register clear pins will be connected to 5 volts, VSS to ground. Ground pins of the shift registers will also be connected to ground, and also the output enable pins of the shift registers will be connected to the ground. The serial input pin of the second shift register is going to be connected to pin 9 of the first shift register. And we also should synchronize the shift register clocks and the storage register clocks. The outputs of the shift registers are going to be connected to the pins of the 7-segment display in the following order. QD will be connected to the 12th pin of the 7-segment display. QC to 9. QB to 8, and QA to 6, 11, 7, 4, 2, 1, 10, 5, and 3. After programming the microcontroller, if we make these connections, our 7-segment display is going to be displaying the numbers between 0 and 1023, which correspond to the ADC conversions of the output of the potentiometer. Now let's check our code. If you'd like to summarize the content of this code, we can say that it's an addition of the ADC module configuration on top of our previous shift register plus 7-segment display code. So I will not be describing the previous part, and I'll be putting that section into a function named display_7-segment, and we'll be sending the ADC result to it to be displayed on the 4-digit 7-segment display. The pin settings will remain in the main function. So let's see the code from our start. Lines 10 to 19 are the configuration bits, and they have been the same since the beginning of this video series. In line 20, we are declaring the display 7-segment function, indicating that it's going to require an integer while it's being called. Lines from 21 to 23 are the same from our shift register code, as well as the numbers, common anode, and the digit arrays in lines 24 and 25. In lines 26 and 27, 2 arrays are defined, which both contain 4 elements. In the main function, we start with the input-output definitions of the pins. GP2, GP4, and GP5 will be the output pins, and GP1 will be an input pin. At this section of the code, I suggest that we go to the datasheet of our microcontroller and see how it's recommended to configure the ADC and how easy it is to implement those recommendations in MPLAB X IDE. Now in the datasheet of our microcontroller PIC12F683, let's go to the ADC module and let's scroll down directly to the ADC conversion procedure. Now we are going to apply this procedure step by step, and you're going to see that it's going to be very easy to write the code in MPLAB. So first thing that we need to do is to configure the GPIO port. And for this, we are going to disable pin output driver, meaning that we are going to set it as an input in the trace IO register And then we are going to configure the pin as analog. We had already identified the GP1 as an input. The next thing that we need to do is to configure it as an analog pin. So this is how we do it. We write down analog select is equal to 1 to set it as an analog input. If we go to the next step, configure the ADC module, first thing that we need to do is to select ADC conversion clock. And for that, we are going to set these values to 0. ADC S2 is equal to 0, S1 is equal to 0, S0 is equal to 0. In the second step, we need to configure the voltage reference. And we do that with this line, line 35. We are setting the voltage reference to VDD 5 volts. And the third thing that we need to do in step 2, let's say, is to select the ADC input channel, and we do that by changing the CHS1 and CHS0 bits. So in order to select 1, we set CHS0 is equal to 1. If we would like to set, for example, A2, then CHS1 would be 1 and CHS0 would be 0. So we can have values from 0 to 3, and these are corresponding to the analog inputs that we have in our microcontroller. The next thing that we need to do in step 2 is to select the result format, and we do that by this line 37, ADFM is equal to 1. And at this point, let's focus on this one. When we set ADFM is equal to 1, and if we look at this figure 9.3, we can see the situations with ADFM is equal to 0 and ADFM is equal to 1. So this is our selection, and you can see that we have two 8-bit registers. First one is ADC result high and ADC result low. And in the ADFM is equal to 1 selection, we only deal with the least significant 2 bits of the ADC result high and the whole bits of the ADC result low. So we get a 10-bit result at the end. However, since our registers are 8 bits, this is the way that we collect this data. And you will see that in our code, we are going to use these most significant bits, 1 and 2, and we are going to merge it with the least significant part. You can see that this is our 10-bit AD result. So let's go back to our steps. We had selected the result format, and we are going to turn on the ADC module. And we do that by line 38, which is ADC on is equal to 1. So we enable the ADC module. We will skip step 3 because we won't be enabling the interrupts, and we will go directly to step 4, and it tells us to wait the required acquisition time. And if we scroll down in our datasheet, we can see the AD acquisition requirements, and in that section you are going to see that the ADC acquisition time is at the levels of microseconds. At the moment, I don't want to go into the detail of this calculation, and you are going to see that this delay milliseconds 10 is going to delay for 10 milliseconds is more than enough for waiting for this acquisition time. Let's go back to our steps. This we already finished, and we are going to start the conversion by setting the go and done bit, and in the code you can see that we are doing in the while one loop. So this is starting the conversion, so we also finish this, and then we are going to wait for ADC conversion to complete by one of the following, following the go down bit, waiting for the ADC interrupt. So since we don't enable interrupts in this example, we will be checking the go down bit, and this is how I do it. I say that if the ADC is busy, do nothing, and our last step is reading the ADC result. Okay, let's again focus on the result format, and you remember that we had selected ADFM is equal to 1, and this is going to be our result format. So what I'm going to do is to get these 2 bits for the most significant part, I'm going to shift these bits to the left by 8 bits. Okay, so this is the 10th bit and this is the 9th bit that we are going to deal. So after shifting them by 8 bits to the left, I'm going to have 10 and 9 and 8 bits after that. And those 8 bits are going to be 0. You can see that these are unimplemented and they are read as 0. So what I'm going to have is all zeros here. And in the code, I'm going to name this MSB variable, and the ADC result low section, which is this one, is containing 8 bits. That is the least significant part of the result. So let's say, for example, question marks. These are either ones or zeros. So what I'm going to do is I'm going to make an OR operation with these two, and I'm going to have as a result the whole ADC converted value. So this is going to be a 10-bit value, and I'm going to name this variable as converted. So let's check this in the MPLAB IDE. You can see that in lines 40 and 41, I'm defining these variables. First one is the converted and the second one is the MSB. And in lines 45 and 46, I'm resetting these to 0. And in line 47, as I described previously, I'm getting the ADC result high value and shifting it to the left with 8 bits. And then first I'm setting the converted as this value, and then making the second OR operation, which was the one that I've already shown, so that I get the least significant 8 bits as well. So after line 49, the converted variable is going to get the whole value of the ADC result. And then when I send it to the display 7 segment function in line 50, that is going to be displaying the value in the 7 segment display. Okay, now let's see our setup again. You can see that we have our 5-volt regulator here, which is connected to a 12-volt adapter, and it's connected to the breadboard. And we've already uploaded our program on the microcontroller, so it's already running on it. And you can see that we have a value of 1023 in the 4-digit 7-segment display. And you can see that our voltmeter is connected to the output of the potentiometer, so we can directly see its value as well. So let me try to change the value of the output. So it's at its highest value right now. So I'm going to try to turn it. And you can see that the value is decreasing on the 4-digit 7-segment display and also on our voltmeter as well. So let's see what value we get at about 2.5 volts. Okay, we are now at about 2.5 volts, and you can see that we have a value of 509. So it's nearly the half of the maximum value. So if we decrease it to lower levels, we see 262, 178, 38, and down to 0. We can see that we are doing a good analog to digital conversion when we compare the value that we see on the multimeter, because our maximum value is 5 volts, which is corresponding to 1023 at its maximum. Okay, now let's try one other thing to make sure that our code is okay. Instead of sending the converted to the display 7 segment function, I'm going to send the MSB value. First, I'm going to save it. I'm going to build it. And after that, First, I'm going to disconnect this from the potentiometer. You see that the values are meaningless right now. And I'm going to connect the PICKit 3 in order to program our microcontroller. And now I'm going to load it on the microcontroller. Connecting to programmer, configuration memory. It's complete. So again, I have to disconnect it. Let's take it this way. Now I'm going to connect the output of the potentiometer again. Let's first reduce it to 0. I'm going to connect it to the analog input pin. Okay, now what we are expecting is we are going to be able to observe the MSB value on the 7-segment display. Remember that MSB value was the first two most significant bits for the ADC conversion. So they are going to correspond to 256 and 512. Actually, what we are expecting is at the level of 1.25 volts, I'm expecting to have 256 value here, because there will be three values that I will be able to observe, and they will be 256, 512, and 768. So those are corresponding to the two digits of the most significant bits. So let's increase the value of the potentiometer's output and let's observe when it reaches about 1.25. You can see that as I reach 1.25 volts, I start seeing 256 on the 7-segment display. And till 2.5 volts, I'm still going to see 256. And as we reach 2.5 volts, as you can see, we are now seeing 512. So the next and last value that I'm going to see is when I reach the value of 3.75, you can see that now I'm seeing 768, which corresponds to 1 and 1 on the most significant bit. And even if I increase it up to 5 volts, I won't be seeing anything because I don't have the 8 bits on the least significant bit side. So this is the maximum value that I can get because I'm dealing with only 2 bits at the most significant bit part. This was the end of the video. I hope it's been useful for you. If you have any questions or comments, please write them in the comment section. Thank you for watching and see you in another video.